Hello and welcome to another IONTOF video. My name is Sven Kaiser and I'm the Sales and Marketing Manager of IONTOF. In today's video I would like to introduce to you our new M6. The M6 is our latest time-of-flight SIMS instrument, and for us the introduction of the M6 that we did during the SIMS conference in Kyoto in 2019 was really a major step forward in terms of instrument performance and instrument capabilities. So this is how the new instrument looks like. As you can see, the M6 comes with a brand new modern ergonomic design. But besides the design, the important factors are of course the performance parts, so the internal values of the tool. So what is new on the new M6 instrument? The M6 comes with a brand new primary ion gun, the Nanoprobe 50. We also developed a completely new time-of-flight analyzer with much higher performance in terms of mass resolution, transmission and capabilities in delayed extraction mode. We also developed a completely new heating and cooling system which gives the user much more flexibility to work under heated or cooled sample conditions. And there are many small refinements in product improvements. So let's start our tour with a new primary ion gun, the Nanoprobe 50. The Nanoprobe 50 pushes the performance of liquid metal ion source and TOF-SIMS further towards the physical limits. We can guarantee now a letter resolution of down to 50 nanometers. We improved the performance in the so-called fast imaging mode from 120 nanometer letter resolution down to 90 nanometer letter resolution. And we could also increase the pulse primary ion beam current from 20 picoamps as it was on the TOF-SIMS 5 to now 40 picoamps. To achieve this kind of performance, the Nanoprobe 50 comes with many small instrument developments. The new column is now equipped with changeable apertures. The apertures are controlled by piezo motors and can be positioned with nanometer precision. So when you change from one aperture to another, there's no beam realignment necessary. The Nanoprobe 50 also comes with a brand new bipolar bunching system, which allows us to get higher primary ion beam currents, but also improves the ease of use of the tool dramatically. The Nanoprobe 50 is also equipped with a new internal Faraday cup. This means that you can measure the pulse primary ion beam current inside the column, so you don't have to go to the Faraday cup on the target as before. This saves you a lot of time, and especially during fully unattended operation it saves a lot of overhead time. So here we have a typical example of the imaging performance of the new Nanoprobe 50. The sample might be well known to you. It's the famous bump structure, the L200, that we use all the time to determine letter resolutions. It's an aluminum multi-stripe structure where the aluminum stripes have different distances. And as you can see in the line scan on the right side, in this example we achieved 30 nanometer letter resolution. One very nice development for the new Nanoprobe 50 is the new bipolar bunching system. So what is a bunching system and why do you need it, and what is the cool thing about the bipolar bunching system? Well, let me explain to you. In TOF-SIMS in general, to achieve high mass resolution, we have to have short primary ion pulses. On a standard instrument, to get the best mass resolution, normally the pulse width of the primary ion pulse is in the order of 0.6, 0.7 nanoseconds, so extremely short. So how can you generate such a short primary ion package? The easiest thing to do would be, if you have an aperture and if you have a deflection system, that you scan the beam over the aperture. When the beam is in the center of the aperture, the beam goes through, you have a target current, you will generate secondary ions. When the beam is deflected, the beam will not reach the target, beam is off, so there will be no secondary ions. With a system like this, you can generate primary ion gun pulses with a width of 1 nanosecond, maybe 2 nanoseconds, something like this. The problem is if you just switch the beam on for such a short time that the resulting primary ion gun current will be very low. There will only be a few ions in every ion package, so your counting rate, your data rate will be very low and you will never be able to get good sensitivity. To overcome this, bunching systems have been used for a long time in time-of-flight SIMS. So what is a bunching system? On the upper side of the slide you see a classical unipolar bunching system. What you have there, you have in principle a condensator. So you cut out a longer primary ion gun package by the system I described before with this aperture and the deflection on the aperture. Typical pulse widths are here in the region of 10, 20, 30, maybe 40 nanoseconds. You let this package fly into the bunching system, and when the package is inside the bunching system, you switch on an electrical field. This electrical field accelerates the ion which are in the back of the package and accelerates the ions which are in the front of the package not so much because they see only a small portion of the electrical field. If you design this in a correct way, you can make sure that the ions in the back just overtake the ions in the front when they reach the sample. By that you can compress a 10, 20, 30 nanosecond package into a sub-nanosecond package. The problem with the bunching in general is that you introduce an energy spread. So when the ions come into the bunching system, they all have the same energy, 15, 25, 30 keV. When they have left the system, they have an energy variation because the ions in the front only gained a little bit of energy, while the ions in the back of the package have gained a lot of energy, typical 2, maybe 3 keV. So all of a sudden you have an ion package which has a large energy spread. This is the reason why the letter resolution that you normally achieve in bunched mode, where you use a bunching system, is not as good as in long pulse mode, because this energy spread will make it extremely difficult for the lens target, which is an electrostatic lens, to focus this package on the sample. Another effect which comes with the bunching is not only that you introduce this energy spread, in addition to that you also increase the average energy of the package. This also makes it difficult for the lens target. The problem here is that if you want to align the lens target, you cannot use a long pulse mode, because after the bunching, so after you've switched on the bunching system, the ions have a higher average energy, which means you have to realign the lens target. Everybody who has operated a TOF-SIMS system knows how difficult it is to get a real good focus and see the focus quality in bunched mode, because there the count rates are lower and then the contrast is not so nice as it would be, for example, in a secondary electron image. So there are two issues with the bunching. First of all, we have this energy spread, and second, we have this increased average energy of the package, which is the reason for the necessity to realign the lens target. So how does a new bipolar bunching system work, and how does this improve the ease of use for the operator? The new bipolar bunching system works very similar to the unipolar bunching system. So also here we have an incoming primary ion package of a certain width. When the package is inside the bunching system, we switch on an electrical field. But here the electrical field is a little bit different because it's bipolar, which means that the ions in the front are decelerated while the ions in the back of the bunching system are accelerated. By decelerating and accelerating the package in the correct way, we can also compress the whole package, so at the end we will reach the same pulse width on the sample, again 0.6 nanoseconds. We still have the effect of the energy spread because we accelerate and decelerate ions. So that's the same with the bipolar bunching system and with the unipolar bunching system. The big advantage of the unipolar bunching system is that the average energy of the package is maintained. So we do not increase the average energy as we did it on the unipolar system. Here we maintain the average energy. This makes now the alignment of the lens target for the operator much easier, because with this new bipolar bunching system, you can align your lens target and the stigmata and all the values that you need to get a good focus quality in a long pulse mode or even in secondary electron mode, so with nearly DC pulses. In this mode, it's much easier to get a good image quality, you have a good contrast, so it's much easier to see for the operator and to evaluate the quality of the image. Then with the bipolar bunching system, you can switch on the buncher, you get the short pulses, but you don't have to do any realignment, and this makes it much easier to use. The effect is shown here on the next slide. As you can see on the classical unipolar bunching system, we can align the beam in secondary electron mode, but as soon as we switch on the bunching system, the image becomes blur because we have this increased average energy of the ion package. So therefore then we have to change the lens target, LT, from the 71% to a higher value to refocus the beam. On the new bipolar bunching system, this is not necessary. So we can do all our beam alignment and focusing in secondary electron mode. Then we just switch on the bunching system and we don't have to do any realignment. So much easier to use. So in summary, we can say that the new Nanoprobe 50 is really a major step forward in terms of performance, but also in terms of ease of use. So let's continue our tour and come to the next major component, the new Time-of-Flight Analyzer. The M6 Time-of-Flight Analyzer really provides a new level of mass resolution, transmission, and especially the performance in delayed extraction mode, the only mode which will allow you to gain or to get the highest lateral resolution in combination with high mass resolution, has been improved dramatically. So what are the new performance figures? The new Time-of-Flight Analyzer provides a mass resolution of 20,000 in the low mass range. In comparison, the TOF-SIMS 5 could get only 12,000. In the high mass range, the achievable mass resolution goes even up to above 30,000. Again, in comparison to the TOF-SIMS 5, where you can get something like 17,000, this is a major step forward. We could also improve the transmission of the Time-of-Flight Analyzer. This will give us higher count rates, faster imaging, higher sensitivity, and so forth. So the new Time-of-Flight Analyzer of the M6 has a factor of 3 higher transmission than the analyzer of the TOF-SIMS 5. We were also capable of improving the field of depth from before 140-150 micrometer to now above 400 micrometer. This is extremely handy if you have to analyze samples with a lot of topography. We could also improve the performance in delayed extraction mode dramatically. So today you can get about 9,000 mass resolution with a lateral resolution of about 50 nanometers. This is a kind of performance which was never been reachable before on any time-of-flight SIMS system. In addition, we could also improve the transmission in delayed extraction mode by a factor of 2. To achieve all those performance improvements, we really started from scratch. So we designed a completely new extraction optics, we extended the flight path, we also designed a new secondary ion transfer system and improved the detector performance. If you look at the results, it's really impressive. So here you see an M6 spectra on a silicon wafer and a TOF-SIMS 5 spectra next to each other. Especially when you look in logarithmic scale, you can see how the new analyzer has a much better peak shape and a much better peak separation due to the higher mass resolution. But also in the higher mass range, here's a spectrum of crystal violet. We can now separate peaks that before we could hardly separate or could not separate at all. The major advantage in general for me using the instrument every day is that due to the higher mass resolution, the average performance I get out of the system without any big adjustment, just by switching the system on, loading a setting file, is also much better. So today with the M6, I easily get mass resolutions of way above 10,000 without a big realignment and a lot of work for me to set up the system correctly. I also get a very good performance on real-world samples. So here you see a typical NIST standard. It's a glass standard. It's rough, it's charging, and even there we could easily get 17,000 mass resolution. Especially if you want to identify molecules, the higher mass resolution is a big help. What you see in this graph is the mass resolution that you can achieve on a TOF-SIMS 5 and an M6 as a function of the mass. The black lines show you the mass resolution that you need to separate certain molecules. For example, if you have a CH or C13 containing molecule and you would like to separate these, on the TOF-SIMS 5 this was possible up to a mass of about 50. On the M6, now all the way to mass 100, we can separate those mass interferences. If you would like to separate a CH2 containing molecule from a nitrogen containing molecule, on the TOF-SIMS 5 this was possible up to mass 150. Now on the M6 you can do this up to mass 300, 350. Besides a higher mass resolution, also the higher transmission of the M6 Time-of-Flight Analyzer is really nice. What you see in this example here are two boron profiles. One was acquired with an M6 in red and the other one with a TOF-SIMS 5 in blue. The rest of the analytical conditions were the same, so we used the same primary ion gun current, same sputter energy, same sputter current, everything the same. What you can see with the M6, you can detect more than 3 times more counts. So you have much higher sensitivity, and this will give you better detection limits. The improved detection limits can be seen in the following example. This is again a boron implant, it's again a NIST standard, and we did the quantification. The detection limits we get now are in the 1E15 range. On the TOF-SIMS 5, this was more in the order of 3E15. So we could directly benefit from the higher transmission of the new M6 to get the better detection limits. The same is true if we look at phosphor implants. The example shown here is again a NIST standard for a phosphor implant, and here as well we did the quantification. So in this example we could also improve the detection limit now for phosphor down to 1E16. The main reason for this is not so much the higher transmission of the system, it's more the improved mass resolution. Because as you might know, if you look at phosphor implants, you always have a strong mass interference on silicon-based systems between the phosphor and the silicon hydride. If you have a mass resolution of 8,000–9,000, this is hardly possible to resolve this throughout the whole profile. But now with the M6 we can do this. The spectra detail plot that you see on the right side of the slide is the spectra from the full profile and not just from a short period within the profile. And you can see that throughout the whole profile you could maintain, or we could maintain, a mass resolution of above 12,000. So this gives us a much better peak separation and therefore a higher detection limit or lower detection limit for phosphor in silicon. The higher transmission is not only useful for depth profiling applications, also for imaging this could be really nice. Here again we analyze the famous bump structure that we have seen before. We did this one time on a TOF-SIMS 5 and then on an M6. For both measurements we used the same primary ion gun, so both systems were equipped with a Nanoprobe 50. Both were run with the same primary ion gun current, same energy, everything the same, and we ran the analysis for 6 minutes. Due to the higher transmission of the M6, within this time frame of 6 minutes, we could again detect 3.2 more intensity. So this means for imaging applications, on the M6 you can run an analysis maybe in 10 minutes that before on the TOF-SIMS 5 would have taken you about half an hour. So you gain there a factor of 3 in measurement speed, or you gain a factor of 3 in higher sensitivity, meaning you get more intensity within the same time frame. Another performance area where we could really improve the performance of the M6 dramatically is the very popular D-lid extraction mode. As I said before, the D-lid extraction mode is the only mode which allows you to gain the highest letter resolution in combination with a decent mass resolution. Just to repeat this, I would like to explain again how D-lid extraction mode works and why this mode is so unique to give you this combination of high mass resolution and high letter resolution. Normally, we work in TOF-SIMS in so-called static extraction mode. This means that when the primary ions hit the sample, the extraction field, which accelerates the secondary ions into the analyzer, is switched on. Therefore, we normally need short primary ion gun pulses, because when the first ion hits the sample, the first secondary ion is generated, and when the last primary ion of the package hits the sample, the last secondary ion is generated. So for a time-of-flight measurement, this means if we have a long primary ion gun pulse of, let's say, 10 nanoseconds, our secondary ion pulses will also be at least 10 nanoseconds long. So this would be very bad for a high mass resolution, because for that we need short secondary ion packages. To generate the short primary ion packages, we can use bunching. But if you remember the slides before about the bipolar and unipolar bunching system, there we introduce this energy spread, which makes focusing not so easy, and the achievable letter resolution is then limited to sub-micron. So in bunch mode, you will never be able to reach 50 nanometer letter resolution. So how can we overcome this problem? Well, we can decouple the primary ions from the secondary ions by using a delayed extraction. In delayed extraction mode, the extraction field is switched off when the primary ions hit the sample. Only after the last primary ion has hit the sample, we switch on the extraction field and accelerate all the secondary ions into our analyzer. By that we can decouple the primary ion pulse width from the secondary ion pulse width. So we can use a long pulse classical imaging mode for the primary ion beam, which will allow us to get the 50 nanometer letter resolution, in combination with the delayed extraction mode of the analyzer, which will give us decent mass resolution. On a TOF-SIMS 5, you could get a mass resolution of about 3, maybe 4000 if you were lucky in delayed extraction mode. On the M6 now, we could improve this achievable mass resolution dramatically. So today you get 9000 mass resolution in combination with the 50 nanometer letter resolution of the primary ion beam. Delayed extraction mode was used for the following example. Here we see small dots of crystal violet on a silicon wafer. The field of view of the image is 10 by 10 micrometer, so we are really operating at the highest letter resolution. Simultaneous to the high letter resolution, we can achieve here now a mass resolution of 13,000 at the same time. So it's this unique combination of high mass resolution and high letter resolution that the delayed extraction mode provides. In the second example, we analyze small bacteria which have been fed with C12 or C13. We can clearly separate the different bacteria. And again, here we have the unique combination of the high letter resolution with the high mass resolution. This gave us a possibility in this example, for example, to separate the sulfur from the phosphohydride or the O2. Because again, we reached a mass resolution of about 11,000 in delayed extraction mode. The M6 analyzer also has a superior field of depth. In the example shown here, we analyzed a commercial adhesive bandage. The bandage was prepared on an aluminum substrate just on the sample holder. The height difference from the top of the bandage to the sample holder is about 300 microns. The total ion image on the right side shows clearly that we have really homogeneous transmission over the whole sample area or analysis field. So we get the same intensity from the high areas as we get from the low areas. The mass resolved images also prove this superior field of depth, because also here we see no shadowing effect. We get good intensity from the substrate, which is really 300 microns down below, and also from the high areas. Also, when we move to a different position where there's no substrate and we just see the bandage itself, we can see that we can get intensity from fibers which are way down in the bandage, and also a lot of intensity from the fibers which are on the top of the bandage. If we run the analyzer in delayed extraction mode, we can also get decent mass resolution on a sample with such a big topography. So time for a short summary. The Nanoprobe 50 really pushes the limits in terms of letter resolution closer to the physical limits. 50 nanometer guaranteed, higher primary ion beam currents for higher detection limits, higher sensitivity. The M6 time-of-flight analyzer is also playing in its own league. Extremely high mass resolution, 3 times higher transmission, extremely high field of depth, and the much improved performance in D-lit extraction mode. The next stop on our tour is the new heating and cooling system. We fully redesigned the sample heating cooling system for the M6. The goal was to have an easy-to-use system with highest performance and highest safety. The new sample heating and cooling system for the M6 allows you full stage movement during the operation. We also increased the sample area that you could use. On the TOF-SIMS 5, the sample area was limited to about 1 by 1 centimeter. Now for the M6, we have about 2.5 centimeters in diameter. The new heating and cooling concept also includes a closed-loop liquid nitrogen circulation pump system or gas cooling on the M6 Plus. It's very easy to use, it's really push button, you have extremely short cool down times, and the liquid nitrogen consumption is with 0.5 liters per hour very low. So you can easily run measurements for a long time without the necessity to refill the dewar. The example shows a temperature-controlled SIMS experiment of polystyrene. So what you see on the left-hand side is the intensity of individual polystyrene oligomers as a function of the sample temperature. During the experiment, the sample temperature was increased by 0.3 Kelvin per second. The spectra on the right-hand side show the oligomer distribution in a certain temperature range. We can see that with increasing temperature, the oligomer distribution goes to higher masses. Besides the hardware development, software is also a very important factor for a modern time-of-flight sim system. With SurfaceLab 7, IONTOF introduced in 2018 a major revision of its software package. At that time we said, totally changes the way we handle our SIMS data. And this is not just a marketing phrase. With a new interactive data analysis, which made data reconstruction a thing of the past, it really changes the way we handle the data. The new version has saved a lot of time for us and for our users all around the world. The upgrade was very well received, and meanwhile more than 33% of all our users have made the switch to SurfaceLab 7. This year, IONTOF will introduce SurfaceLab 7.1, the next major release of its current software package. And this year we can say again, it will change the way how we handle our TOF-SIMS data. Again. So why is that? SurfaceLab 7.1 comes with a fully integrated multivariate statistical analysis package. The package includes PCA, MCR, and MAF. It does not only work on images. The software allows you to do MVSA on spectra, images, and three-dimensional data. As we are about to publish more and more tutorials about SurfaceLab 7.1 on this channel, I don't want to go too much into detail here. I just want to show you one example. The strong point of this new MVSA package is really the full integration into the software. For this analysis, we prepared a piece of paper with 4 different inks. The image on the left is a video image. So you see the piece of paper, piece of white paper, and you see the 4 different inks with different colors. If we now do the MCR analysis, we see that the score images of the different MCR components represent the lateral distribution of the different chemical substances very nicely. Due to the full integration, the software can now directly give you the loading plots of the different components. The loading plot down below is the loading plot of the yellow component. These plots look in MCR very much like SIMS spectra. From the loading plots you can directly see which components or masses correspond to the certain chemical contrast the most. Again, due to the full integration, you can now click on individual loads or masses and see the corresponding secondary ion images. So you are back from the statistical world in the real world and see directly the real intensities. This allows you to directly see if a certain mass contributes to a chemical contrast only of one component or of multiple components. In this example, we see that the masses 7 and 120 are mainly responsible for the contrast of the yellow component, while mass 58 is not only responsible for the contrast of the yellow component, but is also present in other components. This short example should just give you a quick idea about the possibilities of this new extremely powerful tool. For more on this, please follow our coming YouTube videos or install the software and play with this wonderful new tool, which gives you a lot of new possibilities for data evaluation. So time for a quick second summary. I hope I could have shown you that the M6 comes really with a lot of new features. A Nanoprobe 50 with the improved letter resolution, the M6 analyzer with the improved mass resolution, transmission, performance in DLED extraction mode, the new heating cooling system with a higher flexibility and a closed loop liquid nitrogen cooling system. And last but not least, Surface Lab 7.1 with a fully integrated MSA package. One thing which might be interesting for you, if I say fully integrated, it means that it's part of the software. So there are no extra fees that you have to pay if you would like to use this package. It's fully integrated. You don't need any additional licenses like MATLAB versions or whatever. It's part of the software, and all of our 7.1 users have the chance or can use this wonderful new tool. So that's the new M6, the latest of IONTOF's Time-of-Flight SIMS instrument. The product line of the M6 has the standard M6. It also has the M6 Plus, which is our TOF-SIMS SPM combination instrument, and it's also the M6 Hybrid SIMS, so the combination between the Time-of-Flight SIMS with the wonderful Orbitrap from Thermo Fisher. Besides the M6 product line, IONTOF is also offering the TOF-SIMS 5, the QTEC, so our low-energy ion scattering instrument, and a standalone SPM machine, the VLS80. So thank you for watching and listening, but before I let you go, there's just one more thing. What about TOF-MS, the subject the whole community talked about now for quite a few years? Don't you have an option of the M6 which offers the TOF-MS? Of course we do. That's the last subject I would like to talk about. TOF-MS. MS can be a very useful tool. So the capability to fragment a precursor molecule in a collision cell and analyze the resulting fragments can be really helpful. And IONTOF has, with the M6 Hybrid SIMS, an extremely powerful solution for that. The TOF-MS will never be able to match the performance of the Orbitrap in terms of mass resolution, mass accuracy, flexibility in colliding energy, and so forth. But of course, the Orbitrap is also a quite expensive solution. So the TOF-MS can be a kind of cheaper solution to offer some kind of MS capabilities. So when IONTOF started its own TOF-MS projects, there were a few things we had in mind which were very important for us. One thing is, of course, the sensitivity. When we designed the M6 analyzer, we already had the TOF-MS option in mind. So sensitivity was there also a major design target. And with the M6 analyzer and its 3 times higher transmission, we have achieved this already. The second part, which is important for the TOF-MS, is the way how you select the precursor. So we designed a high transmission secondary ion beam deflection system to have the highest intensity also in the MS2 spectra. Conventional TOF-MS systems have a transmission for the MS2 of about 50%, which means only half of the ions that you send into your MS2 analyzer will actually make it to the detection system. The M6 MS analyzer has a transmission of 80%. So instead of 50%, we lose only 20% of the intensity. Still too much, but there's a limit to everything. In addition to the high transmission, we wanted to have a unique precursor selection system with high mass resolution. Conventional TOF-MS systems have a precursor selection system which allows you to cut out or deflect one nominal mass into the MS2 analyzer. If you have the mixture on a nominal mass, or more than one peak, it becomes very difficult to differentiate the different fragmentation spectra, because both molecules or both intensities will have a corresponding MS2 spectra. And if they are overlap or mixed, the differentiation becomes even more difficult, especially if you keep in mind that the mass resolution you can achieve on a TOF-MS system is in the range of a few thousand, not of a few 10,000 or a few 100,000 as you have it in the Orbitrap. So here you see a schematic of our TOF-MS solution. We have our standard time-of-flight analyzer, and shortly before the detector there's an MS1, MS2 switch. This switch allows us to send individual signals into our 90-degree deflection system. After that, the ions fly into a collision cell where the fragmentation takes place. After that, we bunch them together to have a decent mass resolution in the MS2 and accelerate them towards the MS2 detection system. A really unique feature of the IONTOF solution is the 90-degree pulsing system. This pulsing system has two effects. First of all, it allows us to do a very good mass separation of the precursor ion. If you have multiple peaks on one nominal mass, this system allows us to select individual peaks, and the resolution that we achieve with this system is about 3000. It works like this. As you see in the middle, if you have 3 different ions coming into the system at the same time from the top, the 90-degree pulsing system turns them by 90 degrees, so when they leave the 90-degree pulsing system, they will fly on slightly different flight paths. We can then use an aperture at the exit of the 90-degree pulsing system to cut out or select the ion that we would like to look at. The other effect the system has is a virtual beam focusing. This is due to the way the ions are deflected by 90 degrees. So if you have a beam coming in which has a diameter of a few millimeters, and the beam size at the entrance of the 90-degree system is in the region of 1 to 2 millimeters, due to the way the deflection is done, the diameter of the beam in the flight direction is after the 90-degree deflection down from 2 millimeters down to 100 micrometer. So it's a kind of virtual beam focusing. This is quite nice because you have a smaller beam entering the MS2 detector or analyzer, and the smaller the beam, the higher the transmission will be. So this also helps for the high transmission. Let me now show you 2 examples of this new TOF-MS system. The first one is a mixture of 2 molecules. Both molecules have a high peak at the same nominal mass. So in a conventional TOF-MS system, we would not be able to separate those 2 peaks. Due to the unique 90-degree pulsing system, we can do this, and we can generate one MS2 spectra of the first molecule and one MS spectra of the second molecule. As you can see, the resulting MS2 spectra look very different. So you can imagine if you would not be able to separate those 2 molecules, those 2 precursors, it would be very difficult to interpret the resulting MS2 spectra. But due to this nice 90-degree pulsing system, we can do it and get 2 separate MS2 spectra. Due to the high transmission, the IONTOF TOF-MS system is also well suited for TOF-MS imaging. In the example shown here, we use tinovine. You see the MS2 spectra and you see the corresponding MS2 image. Thank you for watching and listening for such a long time, but I hope I could have convinced you what a wonderful machine the new M6 is. It's really a major step forward and we are all very happy with it, and we hope that you all will enjoy it as much as we do. My name is Sven Kaiser. Thank you for listening, and if you would like to learn more about IONTOF and the M6, please feel free to come to our webpage at iontof.com. Have a nice remaining day.